The ocean is the largest predator alive in 4 billion years of evolution. It has killed every dynasty that ever ruled it: trilobites, ammonites, marine reptiles, megalodon. 5 mass extinctions, 1 continent of methane. Once 95% of its species in a geological blink rebuilt from scratch. There is one thing the ocean has never lost: itself. You'd expect that to be reassuring. It's the opposite of reassuring. Cool, right? Because every Save the Ocean campaign starts from the wrong premise. The ocean doesn't need saving. The ocean is fine. What's fragile is us, the version of the ocean we happen to live next to. So how does the most resilient system on Earth quietly decide whether humans get to be part of its next chapter? That's the question, and the answer has already been started. The next 100 years are not a prediction. They're a slow tape rolling. Let's look at the resume first. 5 mass extinctions. 5 recoveries, with completely different cast members. The ammonites didn't make it. Neither did the trilobites. Neither did 95% of the species in the Permian event 252 million years ago. That last one is worth pausing on. How does an ocean kill 95% of everything in it? Doesn't need a meteor. The Permian didn't have one. So what did it have? Temperature change driven by Siberian volcanism, a release of methane and CO2 into the atmosphere. And, this is the part nobody talks about, the slow collapse of ocean oxygen levels. Why? The water got warm enough that it stopped holding dissolved oxygen properly. Currents stalled, stratification set in, the deep layers stopped mixing with the shallow layers. And then the bacteria took over. What replaced the dying ecosystem? Sulfur-reducing microbes, chemosynthetic mats, hydrogen sulfide blooms. The ocean turned, in places, purple and green and toxic. A Strangelove ocean, that's what paleoclimatologists call it. A working ocean, just not one any vertebrate would survive in. Yeah, that's the resume. The ocean recovered. Took roughly 10 million years. So, no rush. Cool, so what's our timeline? That's the part we should be thinking about. The modern ocean is doing 4 things simultaneously, and each one is documented in the geological record as a precursor to bad outcomes. We're not extrapolating, we're just watching the ledger. First, warming. Surface temperatures are climbing roughly 0.13 degrees Celsius per decade, and the ocean has absorbed about 90% of the excess heat humans have generated since 1880. Why does that matter? Because warm water holds less dissolved oxygen. Every degree the surface heats, the entire metabolism of the ocean shifts. Fish need more oxygen at higher temperatures, and there's less to give. The math runs the wrong direction. Quietly. Second, acidification. The ocean has absorbed roughly 30% of all the CO2 humans have emitted since 1800. That CO2 doesn't just sit there. It reacts with seawater to form carbonic acid. pH has dropped from 8.2 to 8.1. Sounds tiny? It's not tiny. The pH scale is logarithmic. That's a 30% increase in acidity in 200 years. So what's that do? It dissolves the structures animals build out of calcium carbonate. Coral skeletons, shellfish shells, pteropod shells. The bottom of the food web is being chemically eaten. Slowly. Like a lozenge. Third, deoxygenation. This is the Permian flag. Modern dead zones, areas of the ocean where oxygen is too low for most animals to survive, have doubled roughly every decade since 1960. There are 415 of them documented now. The Gulf of Mexico has one the size of New Jersey, every summer, like clockwork. The Baltic Sea has a permanent one. So does the Arabian Sea. These aren't accidents. These are the system showing what it looks like when oxygen exits. Fourth, circulation slowdown. And this is the master switch. We'll get there. But first, the part nobody connects. These 4 things don't happen separately. They feed each other. Warming reduces oxygen, acidification weakens the food web, deoxygenation kills off complex animals first, and when complex animals die first, microbes take over the dead biomass, and microbial decomposition consumes more oxygen, which kills more complex animals. The ocean has a built-in feedback loop, and we're feeding it, naturally. So who loses first? In the Megalodon video, we talked about the macro-predator trap. Bigger means more food. More food means a bigger range. A bigger range means more dependencies. When the climate shifts, the giants go first. Every time. Without exception. So who's caught in the trap right now? The blue whale. The largest animal in 4 billion years of evolution. A 30-meter, 150-ton mammal that depends entirely on krill blooms in cold polar water. Krill needs cold water. Cold water is the resource that's disappearing first. The math is simple. To scale a 150-ton predator, you need millions of tons of krill. Take the krill away, and the predator that took 30 million years to evolve runs out of food. In less than a century. How fast is this happening? We have the data already. Blue whale populations dropped 99% during industrial whaling, but they were on a trajectory to recover. Now, recovery has stalled. The whales we have are smaller, on average, than the whales we had 50 years ago. Not because we're hunting them, because their food is moving and shrinking. The macro-predator trap running in real time on the largest animal that has ever existed. It's not going to be a Hollywood extinction. No comet, no asteroid, just fewer krill, smaller calves, lower birth rates. Death by mathematics, death by spreadsheet. No respawn on this one either. Pause on that. The largest animal that has ever lived is being slowly evicted by spreadsheet. But the whale isn't the worst part. Let's go back to the master switch. The Atlantic Meridional Overturning Circulation, AMOC, is the conveyor belt that carries warm equatorial water north and cold polar water south. It is, more or less, the engine of European climate. So why care about a current? Because it's also a key regulator of how the ocean mixes oxygen between surface and depth. When AMOC slows, oxygen mixing slows. When oxygen mixing slows, more dead zones form. Same chain that ran during the Permian, honestly. And AMOC has weakened by roughly 15% since 1950. How bad does it get? Some studies, Ditlevsen 2023, suggest a full collapse is possible between 2025 and 2095, with a central estimate around 2050. Not consensus. The IPCC is more conservative. But less consensus than scary is not the same as won't happen. And here's the thing. When paleoclimate scientists look at the geological record, they find that AMOC has collapsed before. Multiple times. The last time was roughly 12,000 years ago, the Younger Dryas. Northern Europe entered a deep freeze in less than a decade. The ocean rearranged itself. Every existing fishery would have been destroyed. So what does this mean now? We have built an entire civilization on top of one specific configuration of this conveyor belt. And the conveyor belt is showing measurable strain. Slowly. Quietly. While we argue about whether to call it climate change or weather. Cool. So naturally, it gets worse. Because in a stratified, deoxygenated, acidified ocean, who wins? Some species. Just not the ones we like. Jellyfish thrive in low oxygen water and reproduce explosively when their predators, fish, die off. Microbes, particularly sulfur-reducing ones, colonize anoxic zones immediately. Certain crustaceans handle acidified water better than vertebrates. So the new ocean isn't dead. It's just different, smaller, slimier, lower resolution. What's missing in this version? Whales, most fish, coral reefs, shellfish, pteropods. Anything that builds a calcified body. anything that needs a stable oxygen gradient, anything that depends on a food chain that depends on krill, which is, mathematically, almost everything you've ever heard of in the ocean. This is the part most environmental documentaries skip. They tell you the ocean is dying. The ocean isn't dying. The ocean is mutating. And the mutation favors organisms that haven't been dominant since the Permian. The next version of the ocean has been here before, and it ran for tens of millions of years just fine. It just didn't have us in it. So is there anything we can do? Honestly, less than we say, more than nothing. Why less than we say? The mechanical changes we've already triggered have inertia. The ocean has absorbed 90% of our excess heat for over a century. Even if we stopped emitting tomorrow, that heat is still in the system, and it's going to keep changing the chemistry for decades. Acidification doesn't reverse on human timescales. AMOC doesn't strengthen on human timescales. We can slow how much worse it gets. We probably cannot reverse what's already in motion. Not in 100 years. Maybe in 10,000. So what can we do? Decide how much of the existing version to preserve. Marine protected areas, fishing limits, emission reductions, pollution control, none of these stop the underlying mechanism. But they slow how fast we lose biomass, and they preserve genetic diversity. The blue whale, if it survives this century, is a question of how many calves we let it produce while the food situation collapses. That's a policy question, not a physics question. The physics is decided. The policy is what's left. Megalodon ruled the ocean for 20 million years and was killed by 2 degrees Celsius of cooling. We're heating the same ocean about 100 times faster than that. The macropredator trap closes on a different cast every time. But the trap itself is the same trap. And the math of the trap is patient. It doesn't care which species we love. It doesn't care that whales are intelligent. It doesn't care that we wrote songs about them. It just runs. Frankly, the ocean has survived 5 extinctions. It will survive this one too. The question was never whether it survives. The question was whether we and the giants we share it with make the cut into the next chapter. The math says probably not all of us. Probably not the biggest of us. Almost certainly not on the timeline we'd prefer. The ocean will still be here. It just won't recognize us. Next, there's a place in the ocean where this future is already running, where the rules of biology don't apply, where life eats chemistry instead of light, and has done so for as long as anything has existed on this planet. We found it in 1977, and it broke everything we thought we knew about what life needs. That's next, Wednesday.